So I guess I wanted to talk about a number of sort of different topics. This sort of picture of the history of the universe in 21 centimeter is familiar to most of us. So we have this idea of the epoch of reionization at lower redshifts, some period of cosmic dawn, and maybe some cosmic dark ages. There are fluctuations in the 21 centimeter signal, which the various interferometers are looking for. And there's this global monopole signal averaged over the sky that we can also target, which has this nice absorption troughs in the dark ages, cosmic dawn, maybe an emission peak here. And so it's very interesting to look at both the fluctuations and the monopole type signal. So I'll talk a little bit about both of those. So the monopole, or 21 centimeter global signal, started off as this very like cute, optimistic experiment where two people with an antenna could go to the desert with nothing but a dream and detect the 21 centimeter signal. And slowly, these experiments have grown in sophistication. And so, this EDGES result in 2018, claiming a detection of the global 21 centimeter signal, was the sort of the first example of that. But the analysis is still relatively straightforward. You look at the sky, you integrate up, you see the galaxy, you fit some kind of polynomial, and you get some sort of nice-looking or not nice-looking absorption trough, which you then have to persuade the community is a detection. And so as everybody's probably aware, there's a lot of theoretical issues with the sort of EDGES trough, and follow-up experiments like SARAS-3 have so far not been able to detect that. So there's a lot of interest here in trying to come up with robust ways of detecting this global 21 centimeter signal. So I wanted to flag up REACH just a little bit. So REACH is one of these global 21 centimeter experiments. It's deployed in South Africa, in the Karoo, near the SKA mid site. And so this is a picture of REACH. There's a nice serrated ground plane with the actual dipole itself in the center, which you can see down here. So it's nicely solar powered, so very green. And this has been deployed since about January 2024, collecting data with various site trips to fix bits of hardware. And the process is going on of trying to understand the instrumentals of that. And so this is just to show you that there is some data coming from REACH, a waterfall plot with various sorts of foregrounds, FM radio, planes, Orbcom is somewhere down here, the galaxy. And the work, there's about several hundred hours of data collected by REACH now, and a lot of work going on to calibrate the receiver, the beam. And this is just a very kind of crude early spectrum that REACH is seeing. So you can see the RFI, you can see the kind of power law structure of the galaxy. And I point you to some of these very nice papers looking at different techniques for calibrating these kind of global 21 centimeter experiments. So one of the nice things about REACH, I think, is the philosophy is to really try to get a robust detection of the 21 centimeter signal. And kind of key to that is sort of two strategies. So one is, rather than just having a single antenna with a single design, let's try to observe the signal with different antenna, with very different designs as a way of controlling systematics. So each beam will have different chromatic response, different beam. And so by analyzing these together, hopefully you can get a better control of the kind of systematics. And then the overall strategy is to do a kind of forward Bayesian fit for this. So you forward model absolutely everything, the foregrounds, the signal, point sources, the instrument, and throw it into a pipeline and show that it works. So this is just some panels just kind of illustrating that modeling of the data with a polynomial fit, you get these residuals. With some chromaticity correction, you still have some residuals. If you're modeling everything, you can get a nice sort of detection of the 21 centimeter global signal. So this is kind of the route that's being taken. So as I say, so I just wanted to talk a little bit about some of the approaches to that. So there's a number of different papers now looking at modeling different design antenna. So this is from a paper by Anshul Saxena with the sort of beam models for a dipole, conical log spiral, and so on. So different beams, different chromatic response. And you can look at combining those together. And so down in this bottom left figure, so this is integrating the sky over a full 24 hours, so it's one time bin. The graded, shaded region shows how difficult that can be with just a single antenna to get the 21 centimeter signal. If you're combining multiple antenna of different designs, then you can begin to pin that down more. And also, if you use different time bins, that's another way of getting control over the chromatic effects to recover the global signal. So there's a lot of interesting stuff that can be done with multiple antenna of different designs. So there's lots of these different global 21 centimeter experiments now. So we heard about MIST earlier today. So that's a nice portable one that you can move around. We have log spiral ones. We have those that float on a lake. We have things like REACH or EDGES. There are even radio dipole experiments on the moon. And so you might have read about ROLS-1, which landed and then tilted slightly, but it has a low frequency antenna and is able to make some very crude measurements of the spectrum of the galaxy. And there are more sophisticated experiments that will be in lunar orbit, for example, that I think we'll hear about later. So given all of these different sort of experiments, it's worth thinking, are there different things that we could try to do with these kind of experiments? And so with my PhD student, Yordan Ignatov, we were sort of playing about with some of these ideas. So one is to say, well, there's the sky average signal, the monopole, but what about the dipole? So that would be the L equals 0 mode. So we know from observation of the cosmic microwave background that we're moving relative to that CMB background, and that induces a dipole effect. We know the direction of that, we know the velocity of that, and that induces a dipole into the 21 centimeter signal. And you can derive the functional form of that, as has been done in these kind of papers. So it scales with the velocity, it has some gradient of the monopole signal, there's some direction, but essentially the shape of that dipole is exactly fixed by the monopole. And so if you know the monopole, you know what the dipole signal will be, and equally, if you detected that dipole, it would give you confidence that you detected a monopole. So maybe worth going after. The challenge is that the amplitude of this is about 100 times smaller than the monopole signal. So we're talking about a signal around kind of 1 millikelvin. And you can see what that dipole signal looks like in this bottom panel here. And this is just the sky average dipole. It's just hot in one direction and cold in another direction. So what we did was we took this. The idea is that with most of these instruments is you've got some zenith pointing antenna. As the Earth rotates, your beam traces out some track on the sky. And so you're probing the sky at very low angular resolution. And so if you take these kind of 3 different pointings, the foregrounds will be slightly different in each of those pointings. The 21 centimeter monopole will be the same. And so if you were to remove those foregrounds, fitting them with different parameters in each bin, and remove the monopole, you'll get some residuals. And the dipole looks slightly different in each direction. And so potentially that's something that you could try to detect. So we modeled this and did Bayesian inference. And no surprise, it's very hard to do. One kind of interesting thing is that it's actually very difficult to do this blindly with a single antenna. So there's a degeneracy between the amplitude of the dipole and the direction it's pointing in if you just have a single sky track along the sky. So it's much easier if you've got multiple antennae at different locations, because then you can start to localize the direction of this dipole, as shown in this top figure here. But even then, you need lots and lots of integration time to get the sensitivity. So about sort of 10 to the 5 hours. And so this is just a kind of signal to noise plot for that. So with a handful of antennae, probably very different. Maybe you could imagine having hundreds of antennas scattered around different latitudes trying to do this. And that was sort of thing you would probably need in order to get a blind detection. If you're just looking to confirm its existence, and so you can assume the velocity and the direction, it's much easier by a factor of sort of 10 to 50 or so. And so maybe it starts to be in the regime that could be detected in the not crazy future. Okay, so the dipole is very hard because that signal is very small. So what else could you try to do? Well, if you've gone to from L equals 0 to L equals 1, why not go to L equals a few? So if this is the sort of radio sky and you convolve that with the kind of broad beams of these experiments, you get a sky that kind of looks like this. So it's relatively smooth. And if you decompose that into spherical harmonics, then this just kind of sections that out into all of the modes that contribute with L less than 5 and all of those between L of 5 and 32. So the vast majority of the power is in those few low L modes. So you could imagine trying to model these more carefully so that you can separate out the foregrounds affecting the monopole from all the rest, and then maybe having a template for these smaller scale modes and try to analyze things that way. And so that's what my PhD student Jordan did. So you can do a little bit of maths to write this in a linear algebra form. So you've got your A, which is just the ALM of the sky. You've got some beam matrix that describes the beam convolution, spherical harmonics to map you from harmonic space to pixel space. There's a pointing matrix that tells you at a given time where is your beam pointing on the sky. And then probably you average that up into some smaller number of time bins. And so the nice thing about formulating things in a linear algebra way is that then there's a lot of techniques for inverting that from map making in the CMB and other places. So from this kind of data equation, the idea is you're going to try to model the low L sky. You're going to remove a template for the smaller scale modes. But because you're using a template that's probably uncertain, that will add some extra variance onto your noise. And then you can invert things in this sort of a way as a linear problem. So that's kind of the idea. So there you're trying to use some template for the high L modes. And that's not totally straightforward. So the kind of state of the art that we all tend to use is the global sky model, which is just an interpolation between various all sky surveys. What you'd really like is something that really analyzed those data sets in a way that gave you a covariance matrix for the uncertainties as well. So an example of what that might look like is the kind of Bayesian GSM, and this nice paper by George Carter and others. So for our purposes, we just put in a kind of a toy model that would give us some kind of mean template with some uncertainty. And so we did that by taking modeling each pixel with a power law, and then assuming there was some uncertainty on that power law index. And so that's the sort of model of what those foreground pixels look like, and you can derive a covariance matrix from that very analysis. So if you pull all of that together, so the strategy is to try and infer those low L modes from your time data, include the kind of unmodeled high L modes with some template plus extra variance. And then at the end of the day, you can separate out your monopole and then jointly fit that with the 21 centimeter and the polynomial in the standard kind of way. But hopefully, by doing this, you've reduced the chromaticity and the spectral structure of your monopole signal. So you can test that with a simple model. So you've got your foregrounds, some sort of Gaussian absorption trough, some kind of simple model of a chromatic Gaussian beam. And then look at how well that works. And so this is just a sort of a plot of how the error on your reconstruction of the true sky monopole with inclusion of different L modes. And so you need more antenna to probe to higher L modes just to get some sort of angular resolution on the sky. But with three antenna, you can get up to about L of 3. 5 antenna, you can get up to as much as sort of L of 5 or so. And so this sort of reconstruction seems reasonably plausible. So then if you sort of pull that all together, so you can sort of try to compare things in this sort of way. So this very simple case where you've got no chromaticity in your antenna, you have got one 24-hour time bin, looks like this. So you can fit the foregrounds very easily with just a n equals 3 polynomial, get your global 21 centimeter signal. If you include chromaticity, then it breaks everything. And even if you try with sort of naive chromaticity sort of corrections, that's very difficult. And then if you move to having multiple time bins and this kind of low L modeling, then you're able to reproduce the global signal again. And so, essentially what you're getting here is a way of modeling out the chromaticity of the antenna by using multiple antenna and multiple time bins. And so, potentially that's something that's worth exploring, trying to do in practice. Yeah, and so, this is a paper that we're about to kind of put on the archive. We've tested things like increasing the uncertainties on the kind of template that you're using, different levels of chromaticity. It all sort of hangs together. And we're using the spherical harmonics as a basis for describing the sky. That kind of fits in with a kind of CMB background. But that's not the only basis for looking at the sky. And there are other nice models from Anstey and others splitting the sky into different patches for doing that. So there's different strategies that one could potentially use that are interesting. Cool. So then I wanted to segue almost completely just to say a little bit about the inference problem. We've heard a lot about this, and so the kind of general philosophy that we all have is, we're getting upper limits. Eventually, we'll get nice power spectrum, and we want to be able to interpret those in the context of the various models. Those typically produce light cones, so there's a lot more information in the outputs of the simulation than there actually are in the power spectrum that we see. But given our model, we can infer some sort of model parameters, and then maybe also make predictions for other things like the ionization history. And so, this is the sort of game that we all want to play. And there's various challenges that make this harder than it would, we would like it to be. So, things like the evaluation of the models can be slow. So codes like 21 centimeter fast are very relatively fast. There are analytic codes as well. But if you're wanting to compare with the full kind of hydrodynamic simulations, then suddenly you're talking about a very different kind of a problem if you want to do MCMC and have tens, hundreds of thousands of samples. Another sort of aspect, as I mentioned, is so those light cones tend to have more information than is captured in the power spectrum. So we'd like to be able to use multiple summary statistics or even do inference from the field itself to the observations. And so that's an interesting question for us to solve. There are lots of other questions about how well do different simulation predictions match with one another or to reality. And I suppose one of my students, Camille, showed that there can be challenges if you train your machine learning algorithms on one simulation and then try to apply it to another. So in the sort of the little time towards the end, I just wanted to kind of sketch out two machine learning approaches to some of these problems on emulation and simulation-based inference. And that's not my work, but this is work by Romain Mariette, who worked with Benoit Semelin and is now a postdoc with me at Imperial, funded by a STFC DAE grant for UK-India cooperation. So what Romain has done is take advantage of the licorice simulation. So this is a hydrodynamic simulation with ray tracing, computationally quite expensive to do. And so with a budget of a few million CPU hours, that limits you to getting about 10,000 relatively low resolution of these simulations. And so they built up a database of about 10,000 simulations spanning a 5-dimensional parameter space. And so these panels at the bottom just give some indication of the kind of models that are spanned by that. So this is the contribution of the ionization history to the CMB tau. These are the kind of global signals. This is the power spectrum. So there's a range of different behavior captured in those. And so what you'd like to do is to be able to take these suite of hydro simulations and compare them to data. Yeah. And so there's different ways that you can do that. So Tirth mentioned emulation. And so that's now a relatively well-developed technique that people are using. And so in this paper, Romain used a relatively straightforward architecture of dense layers to build an emulator from these Lorelei 2 samples. And you can show that that does a very good job of reproducing the power spectrum from the simulations at the kind of percent level. So these two rows here are a set of different simulated power spectrum for K and redshift, and the emulated result. And by eye, they look almost identical. And if you look at more detail, averaging the data, you can get sort of percent level errors on those. So then once you've got some sort of model that you can evaluate quickly, like an emulator, you can just do your standard MCMC. And so that's what this is showing here, the kind of corner plot for 10 independently trained versions of that emulator. So each time you've got a different random seeds, your training will give slightly different results. And you can see that all of those realizations agree, but there is some variance associated with that. And so ideally, that variance is something that you would include into your Gaussian likelihood to reflect that there's some uncertainty in your model. And that's something that we should always kind of have at the back of our mind. And so if you include that, you get these kind of, somewhere in there's a black contour, which is an even better fit from averaging over the realizations and including that variance. So a technique that's becoming very popular in cosmology these days is simulation-based inference, which is well worth being aware of. So we're used to Bayesian inference with MCMC, where you specify a likelihood and then a prior, and you're drawing samples from that. SBI is very nice because it's a way of avoiding explicitly specifying your likelihood. So provided you've got a stochastic model of your observation, so that you can go from your parameters, include all of the kind of stochastic features of noise, observational effects, to get a model of your data, then the idea is that if you can simulate that, then you can use that modeling process to do your inference. And so the sort of process of that is you draw samples from your parameter from your prior, you simulate your model, you build up a database of parameter sample and data together. So that's giving you samples from the joint distribution of parameters and data. And then you maybe using things like neural networks or mixture models or some other scheme, you can build a model of what that joint distribution looks like. So that's just a kind of example down here where the points are the samples and the contours are giving you some, I think there it's a neural network derived model. So once you've got that joint distribution, you have everything that you need. So if you condition that on the data, then that will give you your posterior distribution. If you condition it on the parameters, that will give you a model of your likelihood. And so the nice thing about this is you can avoid specifying the likelihood, and that's good for situations where you, for example, have summary statistics where you can't easily write down the likelihood, or you want to work directly from the pixel data and the likelihood would be too complicated to work out. And so I think one of the reasons why this is becoming particularly interesting is that the implementations, as they become more efficient, in many cases require less model evaluations than the traditional MCMC sort of exploration. And so just to show an example of that from one of Romain's papers, so this is comparing 3 different approaches for inference. Using an emulator in the traditional MCMC, neural density estimation, where you're inferring the likelihood, Bayesian neural network, where you're looking for the posterior. And you can see that in all 3 of those cases, these come naturally to agree. So this is a noiseless version of that, essentially. So you're just looking at your ability to reproduce the parameters from your simulations. But the nice thing about this is that you've gone from your hydrodynamic simulation that's very slow to run to a setup where you can begin to infer parameters with reference to observations from the kind of upper limits from Hira and Nenufar. And those are things that Romain's been working on. Okay, so I'm about to have the buzzer go off, so I'll finish there. So the thing I kind of want to flag here is that there's a lot of really interesting progress being made with these 21 centimeter global experiments. So with Saras-3 edges, we saw the wide variety of different things. So alongside that, REACH is, I think, a really interesting experiment. I'm biased because I'm involved in it, but it's deployed and collecting data with a view to using different antenna designs as a way of trying to control systematics. And I think one of the things that's really noticeable with the 21 centimeter global signal is this evolution of time from 2 people with a dream to teams working on antenna to maybe now starting to think about creative ways that we can try to analyze this with multiple antenna, either different designs at the same site or maybe trying to explore having different antenna at different sites. So I talked about the 21 centimeter dipole. It's hard to detect, but we know it's there, and so it's worth having at the back of our mind. And my PhD student, Jordan, and I have been looking at this kind of simple idea for trying to map the low L modes as a way of calibrating the chromatic response, removing the foregrounds. I don't think we would say that we have all the answers there, but it seems like an interesting direction to pursue. And I just mentioned at the end, some of the examples where machine learning tools like emulation, SBI, are now starting to allow us to go from the really sophisticated hydro simulations to comparison with data. And I think that will be really interesting in the future. So thank you. I will finish there.
Questions?
Hello. Thanks for the talk. So at the first look, it seems like simulation-based inference will be very expensive because you are not assuming a likelihood and you have to run multiple simulations just to see how your data will be distributed about your model, right? So can you comment on the feasibility of SBI for parameter estimation and how it is being done?
So naively, you might think that it would be very expensive, but but it works, and it works really well. So can I explain that? So I suppose part of what makes it efficient is that every sample that you're drawing. So with techniques like MCMC, you have some you draw, you reject. Not every point is used. One aspect of SBI is that every point is being used in order to give you this joint distribution. And so that's one of the aspects that kind of makes it more efficient.
Very nice. So maybe just a follow-up question on SBI, right? So when you're doing a summary statistics, right? I mean, you can pick and choose what you think is important and maybe robust in your observations against systematics, against model differences, for example, a power spectrum. But if you do SBI, right, you mentioned it already yourself, right? Maybe different simulations have slightly different things, right? You might agree on the power spectrum, but the bubbles are slightly different, the underlying source. So is there a risk in SBI that you are effectively overtraining on details for your specific simulation that perfectly works if you use that simulation to generate data and then to infer the parameters, but where things go horribly wrong if you use somebody else's simulation and further parameters? You see what I mean? So it's overtraining on little things that are not that relevant.
So I see what you mean. So that issue of how well will 2 different people's models agree is a generic problem for any kind of Bayesian inference where you're forward modeling your data.
But is it worse than SBI?
It is no worse than SBI. In some ways, it's made more explicit in SBI. So often, with the traditional techniques, you're writing down a likelihood. And in order to write down the likelihood, you often assume that things are Gaussian, even though you know they're not, just in order to get something that you can write down a simple likelihood and then evaluate it. And so, in the limit that everything is Gaussian, SBI will give you exactly the same results as MCMC, if you run it in the right way. But this can take into account the non-Gaussianity of your noise models and everything like that. I know Andre is chomping at the bit, and I know he has some really nice work looking at this, and comparing the approximations in the likelihood and so on. But
yeah, so I am obviously a fan of SBI. We did a lot of work on this. But I mean, just kind of responding to the previous question, it's not magic, let's say. Like you gain by not having to specify a likelihood, but you pay the penalty in like having, you know, that density estimator, whatever density you're mapping in SBI, that needs to be accurate.
Yes.
And so Roman had a very nice conclusion in his paper where he showed that it's actually less accurate for his density estimator, which was likelihood density for his samples, than the error that you introduce by assuming a Gaussian likelihood in classical inference. We had the opposite because our density estimator, you know, was better. So I think one has to be careful. I think that's the punchline, and there are some nice checks. The beauty of this is there's a nice checks like simulation-based calibration.
Absolutely.
That lets you know if you're overfitting or not, and that's the key thing. So choose your density estimator wisely and do SBC for whenever you're doing anything.
For the benefit of time, if we can move it along and continue discussions after lunch. Yeah. Let's thank our speaker again.